All right, today I spent most of the time talking about the numeric portion of our last lab experiment. In terms of new lecture content, what we focused on was the framing, the setup of open channel flow. And for open channel flow, we're going to think about a solid surface which is inclined to the horizontal at some angle alpha. We're going to assume alpha is small, so that sine of alpha equals tangent of alpha is equal to alpha. We're also going to define the tangent of alpha to be the slope, S naught, so just the actual physical slope of the riverbed. This also means that cosine of alpha is approximately 1. Now, the way we're going to set up our analysis is to consider the variation of the depth. And the depth here we're going to denote by y as a function of x, where the x direction follows the bed. And then we're going to think about the velocity also as a function of x. Now, this is the depth average velocity, or really the cross-sectionally average velocity, q over a. So what we're interested in solving for then in describing channel flow is the variations of depth, the variations of velocity. Now, what are the key drivers of the flow in this case? We've got the weight, which acts downwards, which means there's a component of the weight acting down the slope in the x direction, and then we've got the bed stress counteracting it. If the depth varies, there is also going to be pressure forces. But in the end, what we use to understand the flow in channels is usually the energy equation. And so I'm going to set up an analysis going from point 1 to point 2, where we're using points along the free surface. So P1 over gamma plus Z1 plus V1 squared over 2G is equal to P2 over gamma plus Z2 plus V2 squared over 2G, plus the energy that's lost between points 1 and 2. Now, the pressure at 1 and the pressure at 2 are both atmospheric. And then I'm going to take and write this over here. Z1, referring to the diagram here, the height of Z1 relative to the bed at Z2 is going to be a part due to the sloping bed plus the depth. So we have the sloping bed is S0 times L. That's how much the bed has increased in slope or in elevation from point 2 to point 1, where L is the distance between these 2 points. Plus V1 squared over 2G, that's our left-hand side. And the right-hand side is just Y2 plus V2 squared over 2G plus the head loss. Next, we introduce a new term, the specific energy, which is the sum of the potential and the kinetic energy. And with that replacing depth plus V squared over 2G, we get S0L plus E1 is equal to E2 plus the head loss. And if I let the head loss equal some friction slope times distance, then I can write this as channel slope times length plus the specific energy at 1 is equal to the specific energy at 2 plus friction slope times length. And I'm going to leave it there in this review for today. What we're going to focus on in our next lecture is what happens if E1 and E2 are equal, so the depth is uniform. That means that we equate these two slope terms, and that leads us to a particular relationship. Later, we look at other permutations to the flow, or perturbations to the flow that cause the depth to adjust. But for now, we'll just leave it with this energy balance.